The halogenation mechanism is really similar to the bromination mechanism. Same electrophilic addition, but because it's not Br2 is symmetric, something like HBr is not symmetric. You have an H and you have a Br. So now you have to be a little bit more careful about which atom is being attacked, which atom attacks first or attaches first to the alkene. But it's the same basic mechanism. The double bond is still our source of electron density. That's where the curly arrow is going to originate. And if you think about HBr, Br is a halogen and pulls the electrons towards itself, so the Br is a little bit negative and the H is a little bit positive. So the curly arrow goes from the double bond to the H because that's the more positive, more electrophilic half of the HBr molecule. And then that causes the HBr bond to break. So almost identical to the bromination mechanism, but the difference here is that the double bond has to go at the H and it can't go at the Br. That would be incorrect. So it has to go at the H because the H is the partially positive end of this molecule. But once we do that, again, I'm going to just put it on the left-hand carbon in this molecule. It doesn't matter in this example because it's symmetric. I get my carbocation intermediate again, and I get my Br minus again, and that's our first distinct step. And then in the second step, try to do it quickly. Now we could show that Br minus ion, and we'll put in at least one lone pair, but we can put them all in if we want. That lone pair attacks that carbon, and so that's when the bromine adds. So those are the two things that added. The hydrogen adds first, and the bromine adds second. And now I get my halogenoalkane. Okay, now that was with ethene, which was a symmetric alkene. But not all alkenes are symmetric. So for example, propene, where you have the double bond between the first two carbons, and then there's one more carbon, you can see that it's not a symmetric molecule. That's kind of on one side of the carbon chain is this double bond. So now we actually have to be a little bit more careful, and we have to think about which carbon is going to get the H and which carbon is going to get the Br. And really what it comes down to, and I'm going to skip this Markovnikov's rule for a second and I'll come back to it. What really matters is on which carbon will we have a more stable carbocation. When I drew it for this one, for ethene, it didn't matter if I picked the left carbon or the right carbon because they would both form the same exact carbocation. But when I have propene, I get two different possible carbocations. If the H adds, so we think about these two carbons, I'm going to get rid of the double bond, and I've got CH3 and I've got H. So these are just the four things that are already on the propene. I've taken away the double bond, and draw it twice. So either the H can add here, leaving this one behind as the carbocation, as the positive carbon atom, or the H could add here, and that leaves the left one as the positive carbocation. Okay, so these are our two options when dealing with propene. Got two possible carbocations. Now it turns out the one that's more likely is the first one because of something called the positive inductive effect, meaning, and we talked about this with the SN1 mechanism, when you have tertiary halogenoalkanes, they're more likely to undergo the SN1 mechanism because they are surrounded by more carbon atoms. Carbons have a lot more electrons than hydrogens, and those electrons can be pulled towards the positive carbon atom to help stabilize it. That's what the positive inductive effect is. So in the top carbocation, there's a methyl group sticking off of the positive carbon atom, and so I'm going to draw a little arrowhead to indicate this positive inductive effect. These neighboring carbon, or in this case there's one neighboring carbon, which can help donate some electron density, which can help stabilize the positive charge on that carbocation. Whereas in this one, on the one on the bottom, it only has these hydrogens sticking off it. The hydrogens have very little electron density and very little stabilizing power. So this one on the bottom is less stable, and this one on the top is more stable, Therefore, of the two, the one on the top is more likely to form. And so my major product that I'm going to make is the one where the bromine adds to the middle carbon, not where the bromine adds to the first carbon. So we call this product the major product because it had the more stable carbocation leads to the more stable product, or the major product. This one on the bottom would lead to a minor product where the bromine is going to add here where the positive charge is. So 1 bromopropane would be a minor product, whereas 2 bromopropane would be the major product. So the major product forms based on which carbocation is more stable. And the more stable one has more surrounding carbon atoms with the positive inductive effect to stabilize it. Now, the simple rule, which doesn't explain anything, but it gives you the answer, is called Markovnikov's rule. And it just says that H will add to the carbon atom that already has more hydrogen on it. So if you look at this example, the carbon on the left has 2 hydrogens, the carbon on the right has 1 hydrogen. So I know in advance that the H is going to add here and the Br is going to add here. So Markovnikov's rule doesn't tell us why it happens, but it tells us what is going to happen and what's going to be the major product when we have this halogenation of asymmetric alkenes.